All right, good morning. I have avoided polling you on the extra class because I know many of you are in a flux of deciding which courses you want to take and everything. But I will send out an email by later evening today. So please respond to the email about if you can locate a slot of time for potential extra classes later on. I will discuss this at the end of the class just in case there are students who might be a little late. And also this coming weekend I'll post the first assignment so that you get a little review of the of the materials that we are covering at this point. And that, as I mentioned earlier, best way to learn the concepts would be to solve the problems. So I'll post a list of problems for you. So some of you have emailed me about there was probably some glitch in registration earlier, but now I hope those who want to register are able to register. And some of you have talked to me about the prereqs and such, and I did give you some feedback, but if you still feel as we move along today's class and so on that you want to discuss more, please catch me or find me and we'll have a discussion. And for the same reason, for office hours, I'll also poll you after hopefully you reach some sort of clarity on what courses you are taking this semester and when you're not available. Okay. Okay. So yep.
So will course materials be posted on your website or?
Yeah. So when I send out the request, there'll be a website posted, and all of you will get a link, and you just bookmark it, and yeah, it'll be posted on the website. Okay, so let's see. The end of last class, we were just managed to kind of talk about a bit of review of classical physics or classical mechanics of particles as well as waves. And one of the things we ended up with was that the equations of motion or transport are effectively Newton's laws of motion for classical particles. And just as a form of experiment, you can do pretty incredibly interesting things with just the classical laws of motion with electrons. These are all images of electron beams in vacuum. You can make them go in straight lines. You can make them go in circles. You can do cycloidal motion, all kinds of things, right? So, and I think the two tools you have at your disposal are the electric field and the magnetic field, right? So if you turn off the electric field, you can make it go in cyclotron motion in circles, right? And this is hopefully you have seen many times earlier. It has a certain radius dependent on the magnetic field, on the charge of the particle, and the mass, right? And sometime later in the class, we will see a pretty dramatic consequence of this when you have when you look at this problem in the quantum mechanical realm, where you get the quantum Hall effect and things like that. So it's the same. But then classically, the particle will do circular cyclotron motions. And if you impose on top of a magnetic field and electric field, you can also let it drift. So the whole, the effective location of the electron is going to move because it may accelerate, or it may reach some sort of a terminal velocity. The electron may reach some sort of terminal velocity. So in the first assignment, I'm going to ask you to solve a problem which will kind of require you to apply these classical laws of electron transport, but in a somewhat of a realistic scenario. Hopefully that will give you some, as well, practice of this problem. Right? So what I wanted to kind of emphasize is, in classical mechanics, the path that an electron takes, or for that matter, when I say electron, any charged particle, hole, proton. So electrons and protons are the primary charged particles we know at this point. So both of them take very predetermined or a well-determined path in what we are going to call at this point as a space spanned by the location of the particle, which is x in one dimension or r in 3 dimensions. and the momentum, or in some sense, the time derivative of this, dx by dt times the mass, right? So that's the velocity. Velocity times the mass is the momentum. So this is the momentum and space, space, if you might. But we'll see towards the end of the class today that the momentum for motion in quantum mechanics becomes intimately tied to the phase of a wave. So the momentum, both for photons as well as for electrons, the momentum times the distance, the product of this becomes a phase. Momentum divided by Planck's constant. So it's k, 2 pi by the wavelength of that particle. So this will become 2 pi by the wavelength. So that's 1 over length. That's length. When you take the product, it's dimensionless, and that's the phase of a particle. So the angular frequency. And so typically this is also called the phase space, and x and p. And kind of one of the defining features, if you might, of the classical motion of particles is the motion in phase space is deterministic. The path is deterministic. When you apply any sort of electric field, any sort of magnetic field with some sort of an initial velocity here, you can really track its path if you know the electric field and the magnetic field. If you know the two, then you can completely determine its essentially its future completely. At any point of time in the future, you know where it is going to be moving with what velocity. So that really is what is used to. I think you can probably appreciate how powerful this law is. This is really still Newton's law of motion, but you can launch something from from the Earth, and it lands on Mars or somewhere, and that all of that uses this law, right? So it's very precise. But of course, when we go to extremely light particles moving in very potentials in crystal are very rapidly varying and so on, then this law fails. It is unable to explain many of the phenomena we measure in transport in such scenarios. And that's where, that's essentially trying to motivate why do we need the quantum in this aspect, right, at this point, right? So in classical mechanics, I'll just kind of do a couple of things, and these are concepts that are regularly used in understanding transport in solids, in metals, amorphous solids, or for electrons in semiconductors and so on. Towards the end of the class last time, we started with the relation that the rate of change of velocity was equal to the mass times the velocity was the force. That was Newton's law, right? And then what we said was, so the force for us was the electron charge times an electric field, Q times E. Right? Let's say it's positive charge, or if it's negative charge, this is minus 1.6 times 10 to the minus 19. And we also said that there is, if you impose some obstructions in the path of the electron, there would be a rate at which the momentum, mass times velocity, can be lost to scattering, to that sort of thing. And we kind of we basically merged all those complicated concepts of scattering, how much time it will take between two scattering events, that's the tau, into this parameter tau. Okay? And from here, we could see that right away the steady state situation, when nothing changes with time anymore, all d by dt's go to 0, the velocity is equal to a kind of a lumped parameter times the electric field, and the velocity becomes proportional to the electric field. So, and this is the mobility of the charge, if you might. Right? So what's called the mobility. And mobility is effectively a classical concept, but to calculate, we do know typically the charge of the electron very accurately, right? The mass will go a little bit of transformation once we put it into a crystal. It will become an effective mass. And the scattering rate we will develop concepts in this course by which we can calculate the scattering rate from completely quantum mechanical considerations. We will develop some aspect, that aspect of the story in this course. But regardless, if you look at it, mobility has units. From here, you can see that the velocity, we will be using centimeters per second. This is a sort of a mixed bag of units, not quite SI. You can do meters per second, but centimeters per second is what typically is used in most solid state materials. Electric field is volts per meter, but we generally use volts per centimeter. So it's somewhat of a relic of large devices from some time ago. And so you can see from here to dimensionally, the mobility should have units of velocity over field, which is centimeters over second over volts per centimeter. So it has a weird looking unit, centimeter square per volt second. Right? So that's the units of mobility of charged particles in actually any sort of situation. It doesn't have to be even in a solid. You can define the mobility of an electron going through a gas, and it can collide with the gas molecules of the gas, and you can define an effective mobility this way as well. So it's a very generic concept. Okay, so in fact, an ion moving through a charging of a battery, for example, batteries are charged with lithium ions moving across interfaces, can define a mobility for the ion as well. Any sort of situation where you have a charge and a mass of particle that's moving with some in some sort of a medium that scatters, its concept is very generic. And it's a classical concept. Just to get a feel for what sort of numbers are we talking about here, typically the electron charge is something we should be very clear about. 10 to the power minus 19 coulombs, right? 1.6 times 10 to the power minus 19 coulombs. The mass of a free electron mass, let's call it M0, is 9.1 times 10 to the power minus 31 kilograms, right? So that also we know. In most crystals, instead of the mass, we will have an effective mass where instead of a free electron distribution, the effective mass, sometimes labeled as M star or M, typically of the order of maybe, if I take silicon, in silicon the conduction band effective mass is roughly 2/10, or 1/5 of its mass in free space. So it feels a little lighter in that sense. And that's an order of magnitude depending upon what material you are in. This quantity is a measure of what we call as the energy band structure. We'll talk about those things later. And I'm saying we'll talk about it later, but I think I hope most of you have seen those things in some sort of a solid state physics or course like that. But we will again review those concepts. Okay? And typically a scattering time in a solid is what order of magnitude? Anybody has an idea? How if I have electrons moving through, say, a semiconductor, what's the typical rough order of magnitude of how long does the electron move before it scatters?
Picoseconds.
Sorry? Picoseconds. Yeah, sure. Yeah. So yeah, I would say picosecond is a good number. I mean, roughly 10 to the power minus 12 seconds is the order of magnitude. Okay. So roughly a picosecond, and I would say that so you can combine these and get let's just do this for these numbers how it looks. I'm going to throw out all the factors of 1 at this point. 10 to the minus 19. Let's say that's 10 to the minus 30, right? And this is 10 to the minus 12. And what we are going to get, these are all SI units. You can see we are going to get this in meter square per volt second. You can check that. And this is something that if you are not doing transport all the time, you may make sure you're always comfortable with the units. And when you look at a number, I hope as you go through the course, you will realize that this is wrong, meaning it can't be true from physical considerations and things like that. So you can see here, what will I get? Okay, so roughly 21, so maybe 0.1, right? Meters square per volt second, right? Order of magnitude, you can take care of all the other things. And that is, if I want to convert from meter square to centimeter square, just multiply by 10 to the power 4. That gives you about 1,000 centimeters square per volt second, right? And that's a good order of magnitude of mobility of electrons in silicon, for example. It's a good order of magnitude when you measure it. This is roughly how much you will measure for electrons in silicon, for example, right? Now, it's very easy to say all these things now because people have spent the last 5 decades, 50, 60 years almost trying to measure this incredibly accurately, and they still are measuring it because silicon is an extremely important material. They're measuring silicon, measuring it all kinds of semiconductors, in metals, all kinds of things right now. So as we move along, we will kind of take apart all these separate quantities that or parameters that we are plugging in here and look deeper into each one of them in the future, except at this point, except for the charge, we're going to look deeper into the mass and the scattering rates. Okay, so any questions about this point? Yeah, please.
How much does the scattering time change when I'm going from metal to an insulator?
Good question. So in a metal, it really depends on which ones we are talking about. For example, a copper has very long scattering times. It has very high conductivity. So whereas there are some other metals which will have. So within metals itself, you can change by at least an order or maybe more. But if you go to the highest mobility semiconductors, so for example, at room temperature, some semiconductors like let's say indium arsenide, instead of 1,000 centimeters square per volt second, you can get up to 40,000, so 40 times more. That's because of two things. One is the mass is lighter, and second is the scattering time is also longer. So you make it purer and purer, and you can keep increasing it. So that's just the room temperature mobility at 300 Kelvin of the order of, say, 40,000 centimeters square per volt second. It could be larger. I'm just an order of magnitude at this point. If you take it to low temperatures, on the other hand, the mobilities can go into a few millions, 10 million, and then the scattering time could go from picoseconds to, it could easily get into almost microseconds. So then the electron would move, even though it's inside a solid, it would move almost centimeters, I would say at least a millimeter without a single scattering event. So that's ballistic transport. It can move that way, and those are the conditions which we see much of this quantum transport phenomena. Where so the generic concept of this course would be that the quantum transport will show up in extremely pure samples or at low temperatures. As you introduce more and more scattering, you end up in classical transport. So as you introduce and you dephase the wave. The phase of the wave function and all that. So, okay, any other questions here? All right, so if not, so there's a whole range of semiconductors and metals, and we will discuss them as we go along, right? And I shouldn't forget to say, because that's a topic we're going to cover in this course, that and these are. This concept has a tough time surviving if you go to a superconductor. It's very difficult to apply this concept in a superconductor where electrons pair up and form Cooper pairs and such things. So that there are limits to how far you can push this model. The second thing I wanted to add here, which are relatively simple concepts, is once I have velocity. As you know, the traffic in any highway is not just determined by how fast is one car moving, right? It's actually not quite that much. I mean, it's much. What's the other factor that's missing here? If I want to find the current, if current that flows inside any solid or any part of space, right? Again, this is I'm not asking a very difficult question at this point. So let's say cross-sectional area is A, and length is L. And you have a beam of electrons going in, or beam of charged particles going in. So the current, as you know, is will be the voltage divided. The resistance times the current is equal to the voltage. And the resistance itself, how is it determined? By the geometry of the whole object in classical physics. The resistance is what we call as the resistivity times the length over the cross-sectional area, right? And this is also a very classical concept where you have a lot of scattering. If I have ballistic transport, we'll see later that even this has to be modified. There's a factor that doesn't change with length anymore. So as you make the thing smaller and smaller, the resistance will decrease. So the resistance of a semiconductor chunk which is doped as a function of length, according to this, should decrease. It will decrease, but then it will kind of level off at some point. And that is of the order of what we call as the mean free path, and the distance an electron can move without scattering. So below that, there's no change in resistance because the origin of resistance is scattering, right? So if you take that out of the picture, there's no. So and this is something that is today measured in most transistors, electronic transistors that we make, where the distance that an electron has to go from the source to drain is about 10 to 20 nanometers. So that's already smaller than the scattering length, length over which you can scatter. So therefore, the resistance is not going to zero, is what I kind of wanted to really say. So it actually saturates, and we'll see those things. So so the resistivity is also defined. It's 1 over the conductivity. Right? That's the definition of these things, and the conductivity is, I think that we can write down without by intuition, that the conductivity of a beam of electrons is, let's for simplicity at this point assume all of them are moving the same velocity, right? Then the conductivity would be the electron charge times the velocity times the number density, right? How many electrons are moving, right? And that's what I said to gauge. So the actual traffic or the actual current or the flux of particles is really dependent on how many particles there are. Right? So you could have a very high velocity, but if you don't have enough population of those carriers or electrons, then the conductivity is very low. So the electrical conductivity really depends on both. And this is a kind of an important point, because in the quantum version, it will also show up. You have to sum over many k states, for example, to find out how many particles there are, right? And then you can. So in general, if we look at more microscopically, you can sum it over many, classes of particles that are moving. A bunch of particles are moving with, say, a certain velocity. Another bunch are moving some others. So you just sum the whole distribution. Right? And what quantum mechanics will also impose is this carrier density must follow the exclusion principle, the Pauli exclusion principle, which will result in the Fermi-Dirac distribution of carriers, right? So you can't fit all of them moving exactly in the same velocity in some direction. It's not possible for fermions. So we'll see all those things. Yeah. So yeah.
And the formula for conductivity, should it be V, or is that mobility, or is that?
Oh, I'm sorry. Yeah. Thank you. Yeah. Thank you for correcting me. Yeah. So this is. Actually, all right. Let me change it. I jumped ahead. Right. The mobility is Qn times the the conductivity is charge times density times the mobility. The current density, which is current over the cross-sectional area, the total current flowing I divided by the cross-sectional area, right? The current density, that is equal to the electron charge times the electron density times the velocity. So the current is really the physical meaning of the flux of cars on a highway, or whatever particles in through a wire or something like that. So yeah, thank you. Yeah. So conductivity has mobility in it. It doesn't. The way it's defined doesn't depend on the electric field, so at least at this point. And the current density is that. And again, orders of magnitude here would be, let's see, what would be the units of, if I take our definition of mobility here, I'm going to drop the negative sign. I hope we are comfortable with that. It's Q tau over mass, and mass has the right meaning. If you're in a solid, it's the effective mass. Right? And so the velocity we already found was mobility times electric field. So that becomes Q times N, right, times Q tau over mass. And velocity is mobility times electric fields, right? So this whole thing here, which is Q square N tau by the mass times the electric field, this whole thing here is equal to this. It's the conductivity, you know. So in other words, current density is conductivity times the electric field, right? That's a classical transport law. And this is really also your Ohm's law in disguise, right? You just take this and you multiply J with A, and you conductivity, electric field is actually voltage. If your voltage drop is uniform across a material, voltage over length is electric field times the right. So and then from here you can see that times A, and you combine these things and you get your I is equal to V over R, right? So that's Ohm's law. It's the same thing, right? So it's slightly more microscopic picture of the Ohm's law, but not yet completely a quantum picture. Orders of magnitudes of currents. So this is an important quantity. Typically, let's talk about a semiconductor first. In semiconductors, the carrier densities in a doped semiconductor, what's the typical order of magnitude? You know, let's say I take gallium arsenide or silicon. What's a typical three-dimensional doping density? How many electrons are participating in transport typically in a conduction band? Let's say it can be many. It can be nothing. It could be highly insulating. But let's say I have doped it N-type. I put some electrons in the conduction band. What's the order of magnitude of the carrier density? 10 to about 20 per centimeter cube. So that would be on the higher side. That's kind of a very heavily doped semiconductor, but very much, I mean, you can get that, yeah. So N, I would say maybe let's look at a slightly lower doping density, maybe 10 to the power 18 per centimeter cube is also considered to be a heavily doped semiconductor. And from here, if I were to take that and say the velocity is equal to mobility times electric field, and mobility we said is of the order of maybe 10 to the power 3 centimeters square per volt second. Electric field, let's get a fair idea of what would an electric field look like in a piece of semiconductor if the distance from here to there was roughly, let's say it's about 1 micron. Today's devices are much smaller, like 10 nanometers or so, today's devices. But let's say it's about a micron at this point for discussion. And we apply across it 1 volt. 1 volt of, we connect a battery to both sides and apply 1 volt over a micron. So what's the field then? Order of magnitude again. So that would be 1 volt over 10 to the power minus 4 centimeters. That's 1 micron. It's volts per centimeter, right? And so you can see from here, the velocity, what's the order of magnitude? 1 volt. And then, your volts, centimeters cancel. I'm just doing some basic stuff here. Okay, so it's about the order of 10 to the power 7 centimeters per second, roughly. And that's a fair order of magnitude for a little bit on the high side of velocities. This is a bit on the high side. This is what's called as a saturation velocity, and I'm going to talk about that now. But electrons in semiconductors typically would be moving, if you have a slightly lower electric field at 10 to the power 5 centimeters per second, 10 to the power 6, 10 to the power 7 centimeters per second is a good order of magnitude when a transistor is on, for example, when you want it to be flowing current. Electrons on an average are moving at this velocity. But very soon we'll see that this number hides behind it a lot of details. In fact, when we throw all the quantum on this subject, what we'll see is there are some electrons moving with 10 to the power 8 centimeters per second going from here to there. Some that are actually going very fast but going perpendicular to the field. Some of them are going backwards. So when you sum all of them, the effective average is this. So we're going to see that very soon. So it's always a distribution of carriers that are doing, going in many directions, and The sum total of all of them is this. You can really collimate them. For example, if you take a carbon nanotube or something like that, where you force them to only go in one direction. Then you get a much more collimated beam of electrons inside a solid. But in general, in a three-dimensional material, they will be going in all directions. And this is the sum total or the average of all things. So with that velocity and this carrier density, what would my current density be in a semiconductor? Again, Q times N times V. That's don't do this. This is just for me in class. I'm going to say charge is 10 to the power 19 coulombs, 10 to the power 18 coulombs, and then this is 10 to the power 18 per centimeter cube. The charge is 1.6 times, just for argument's sake at this point. 10 to the power 7 centimeters per second, right? So that gives you a fair idea of how much current density is flowing through this material, right? And it's good to have these numbers in mind, because when you do calculations, you may see that, oh, I'm 6 orders off, then there's something wrong. So okay, so what does that turn out to be? About 10 to the power 6, 10 to the power 6, and current density, as you know, will be amperes per centimeter square. Current per unit area, right? So coulomb per second is amperes, charge per unit time is amps, and centimeters cancel out to give you centimeters square, right? So and this I would say is a mega amp per centimeter square. That's the number. 10 to the power 6 is mega, right? Mega amp per centimeter square. This is actually a pretty high current density in a semiconductor. Typically, in a semiconductor device, this is a current density. For example, you need in a laser. In a laser, you'd be talking about 100 kiloamp per centimeter square, almost approaching mega, but not quite. In transistors, in a two-dimensional electron gas, if you divide by the very thin quantum well thickness, this is roughly the order of magnitude of current that flows inside the material, right? So roughly order of magnitude. So in a metal, so is that clear? I mean, this is so meaning I'm saying that if you see in any sort of calculation you are getting 10 to the power 10 to the power 15, that's wrong, because what happens is these particles, in fact, most solids are it's not possible to push more than about 10 megaamp per centimeter square through any solid. And the reason is the electrons have so much momentum then that they collide with the atoms, and very rapidly and with a lot of energy, and they start breaking the solid itself, the bonds of the solid itself. So in making transistors in early 2000s, one of the big change it was when the currents, but you can imagine if you have the number of transistors has increased over time, right? So the number of transistors that are kind of sitting down here, very small ones, have increased over time. And to access each transistor, you must flow current, that sort of J, through all these metals and go into that transistor and then do some logic there, 0 or 1 there, right? But you have to access them. And the electrons flowing in these metal interconnects, that's the word. If the current density goes slightly over 10 megaamp per centimeter square, it causes what the problem is known as electromigration, meaning with a very high current, these wires, which used to be aluminum, basically the current would move the atoms, and then you have a void, and slowly the resistance increases, and then it becomes open. There's no more current anymore. So that's what force. Because you have a lot of transistors and each of them need roughly the same current, right? And so the current carrying capacity of each of these wires must go up, right, with time. And with scaling, so early 2000s, these were replaced with copper, because copper had much higher conductivity, and it had a more resistance to electromigration and things like that. So that was one of the reasons why it got changed to that. Okay. So you can obviously have lower than this with a smaller electric field or less carriers. You can have lower, but much higher is typically not possible. Typically. On the other hand, in vacuum you can have a lot more, because there's nothing to migrate. In vacuum there are no atoms, right? So you can have a lot more current density in vacuum, but in a solid you are restricted a little bit because of this. So we did this for semiconductors, but in a metal, the game changes a little bit in terms of the ratios of these, and I think also kind of in answer to the question you asked, the carrier density in a metal. What's the typical carrier density of mobile carriers in a metal? Order of magnitude again. Yeah, so it's 10. So Joey said 10 to the power 21 to 22. It's roughly order to the atomic density. Each atom, give or take, contributes 1 electron to the conduction in the metal. And we will again discuss density of states and other things like that. But in a metal, we are looking at 10 to the power 22, 23 sometimes per centimeter cube carriers. Right? But the current carrying capacity of a metal is not too much higher than in a semiconductor. It's not too much higher. It is higher, but not too much higher. Typically, the scattering times of that you might get in a effective scattering time in a metal would be much shorter, and the current densities would again come out to be about 1 to 10 megaamp per centimeter square, not much more. So tau has to scale down accordingly. The metals, if we look at what's called the Fermi surface of it. It's a little more complicated than the semiconductor as to exactly how you explain this phenomena. But all this theory was first developed for metals, and then we are just applying it to semiconductors at this point. So yeah. Okay, so the last thing in classical sort of transport I wanted to add here, which is actually a very important concept, is this seems to indicate that if I take this picture, velocity is mobility times electric field, and I were to plot the velocity of electrons that I have measured by some means, and we will talk about how you can measure it as a function of the electric field, that it should be basically a straight line, right? I mean, it's with the slope of the mobility. V is mu times E, right? So it should be a straight line. But when you actually take a piece of silicon or gallium nitride and you measure it, it will indeed start out like that, but very soon it will saturate. It won't keep going. There's a relativistic speed limit of speed of light, but this is much smaller, this side, and reaches what we typically refer to in the jargon as the saturation velocity. And this is what I was trying to kind of get to, is of the order of maybe 2 times or 1 time. But again, this is a higher end of the spectrum. Typically, this is what it reaches, roughly like that. It's the higher end. And if you're moving at 10 to the power 6 centimeters per second, 10 to the power 5, you are still in a linear regime. And Ohm's law is valid here. Ohm's law is not quite valid there. Right? So you can see that here, if you change the electric field by changing the voltage, the velocity is not changing anymore. So it's saturated. Right? And the reason for that is what? Why does it do that? So it's a non-ohmic behavior now. Yeah. Anyway, yeah.
As the electrons moving faster, tau changes?
Yes, effectively you can think of it that the tau has changed, and it's scattering more often, right? But so what mechanism why does it do that? That's correct,
Yeah.
indeed.
I mean, it's just like moving faster, so
Yeah.
more kind of chances to scatter per second.
Indeed, yeah, and so the particular scattering that goes up a lot is the electron starts colliding with the lattice itself, or the crystal, and it sets off emits phonons or phonon vibrations of the lattice, right? And so this is a sign of electron-phonon interaction, which will be a major topic in this course, right? Electron-phonon interaction. In fact, you can also get a very quick estimate of what should those, why should the saturation velocity be of that order of magnitude. We can get that, and let's do that just as a back of the envelope calculation. So what we are doing here is the qualitative picture of it, and for quantitative details we have the entire semester to figure out, and bother about what is exactly tau, what is all that. But qualitatively, this is the idea. So the electron starts out, let's use perhaps another board. So we are trying to explain, so let's say the electron starts out and you have all the atoms in its way in a periodic lattice, right? And as it moves, so typically the length of a chemical bond inside a solid, what is the typical length of a chemical bond, distance between two atoms? Yeah, a few angstroms, maybe 2-3 angstroms or something like that. So let's say 3 angstroms, right? Now let's look at it from again a very intuitive or classical picture. If the electron was 5 angstroms big, it can't go, right, in principle, right? Right? So what is the, this is an interesting question. What is the size of the electron? Do we know? What is the radius of an electron? Yeah, and it's actually never measured. I mean, it's a point particle, which is very weird. I still find it very disconcerting, but it is a point particle. It has really no radius, right? You can go and do some sort of analysis with relativity and all, get some sort of an effective radius, but there is really no radius to the electron. You know, it's just a point particle. So from that perspective, you can see it should be able to go through, right? I mean, from that perspective, you know, this is an infinite swath of space and no problem, right? It's a point particle. So, and actually the most amazing thing about transport in solids is the fact that electrons move through a solid almost as if there was nothing in its way. You know, but of course, the laws of motion like mass and all those are determined by the crystal it's sitting in. But other than that, it's and that's basically the Bloch theorem and others. We will talk about that. But okay, so as it moves through, if it's moving very slowly, if you are in a low velocity regime, if you are out here, it doesn't have enough energy to set off lattice vibrations. Typically, the lattice vibrations come in two kinds: acoustic phonons and optical phonons. Let's talk about optical phonons for simplicity at this point. Optical phonons we'll call it h bar omega optical. When we quantize it, it will be in packets of, you know, quanta of one optical phonon. So order of magnitude. So what is it? Essentially, it is classically the electron goes and maybe collides with this, and because you can think of this whole crystal as a mass spring system, right? It's mass spring. So if you pluck one, the whole thing will start vibrating, right? Now it has all these normal modes. You can kind of it has all kinds of modes. If it hits it this way, the wave will kind of go that way, right? To conserve momentum. But you can break it up into, you know, all kinds of normal modes, and each one of those modes will have roughly the energy of h bar omega here. You know? So that's the quantum picture of that. Yeah, we don't have to worry about that aspect right now. What I wanted to get to is the optical phonon energy of most crystals, you know, like silicon or gallium nitride. What is the order of magnitude of optical phonon energy? Do you have an idea? Of most solids. So this is kind of the threshold energy. If the optical phonon energy is h bar omega and the electron has only, you know, 1/5 of that energy, it cannot set off that vibration. So there's a little threshold for it to set it off. You know? So yeah. So order of magnitude of optical phonon energies is typically 50 millielectron volts, MeV, millielectron volts. So about 50 depends. I mean, this is order of magnitude. I think silicon is 63, gallium arsenide is 30 something, 36. So the lighter the atoms get, the larger is the optical phonon energy. So diamond or graphene would be like 180 or 200 MeV, you know, 3 or 4 times that. Yeah. Heavier is the atom, like indium arsenide, that would be like 20. So it's you can imagine even intuitively that the frequency of vibration depends on mass spring system is k over m, where k is the spring constant, and heavier is the mass, you know, lower is the frequency threshold for these vibrations. Okay, so the reason I'm kind of discussing this in a little more detail is because what we are trying to explain is why does the current saturate or the velocity saturate, and if you have an optical phonon energy threshold like that, you know, and the energy of an electron is, you know, half, again, very classical picture, half mass velocity squared, you know, kinetic energy of the electron. And if we track the velocity, or let's say we track the energy of the electron with time, right? Velocity as a function of time. You can see that if I have an electric field that's driving the particle in that direction, or the force, let's say, is driving the particle in that direction. So it's going to go along, and the velocity, let's say, or the energy, you can see, you know, v square, energy is v square. Velocity, let's say, starts from 0, and then it accelerates, right? The velocity will increase with time, but then it will reach, at a certain point, the optical phonon threshold, right? And then it's now ready to collide. It has a very high probability of scattering and emitting that optical phonon now, right? So the moment it collides, It can do many things, but meaning it can recoil, go backwards, it can scatter at an angle. But essentially what it does is the ones that will kind of affect your transport the most are the ones where your velocity, it loses most of its excess energy to the optical phonon, because energy is always conserved. If it collides and it has set up an optical phonon, the energy is now not in the electron system, it's in the lattice vibration, right? So the energy is lost. Yeah, sure.
Why is the optical phonon the limit here, not acoustic phonon?
That's a good question. We will look at that in detail. Acoustic phonons do play a role. I'm trying to hide that a little bit under the carpet right now. And the reason is because in magnitudes, the optical phonon scattering rate is way higher than the acoustic phonon near the energy thresholds and all that. At extremely low energies, you can start emitting acoustic phonons too. But acoustic phonons have very low energies also, so it doesn't take away that much energy. And typically, it's kind of a quasi-elastic almost. Most of the energy that the electron loses goes into optical phonons first at a high field. So that's why I'm focusing on that. But acoustic phonons are also involved. Their effect on the saturation is lower than the optical phonons. So and we'll look at that in more detail as we calculate scattering rates and all that. Okay? So any other questions? All right, if not, so essentially the simplistic picture one can think of is the velocity increases. I'm drawing it in this way. It could be linear. I'm just sketching, but then I can imagine it drops, increases, drops, increases, drops. So that's one way of looking at it. So every time it accelerates, collides, sets up an optical phonon, emits an h bar omega here, loses that much energy right away, and then accelerates again, loses h bar omega, and that's it. So now you can take this and convert it back into velocity, and you'll find that there'll be some sort of an average velocity here that it reaches. Doesn't matter, the average energy converted, and that's what we are typically referring to as the saturation velocity. That's why it doesn't go any further than that. And this picture should tell you why. I mean, this is very, I think, clear why the velocity won't keep going up. Now, from here, you can show that the saturation velocity would be of the order of square root of the optical phonon energy over the mass of the particle. Again, there may be a 2 or a pi sitting there, but that's the order of magnitude. So roughly that's the order of magnitude. And in a semiconductor, again, you can plug in these numbers, maybe 50 millielectron volts over, say, 0.2 times the free electron mass, and you will end up with roughly 10 to the power 7 centimeters per second here. So that's so it's kind of important to realize that the saturation part of the velocity is really an indication of essentially this is because of phonon emission, and an electron is setting off all the vibrations in the lattice and dissipating its energy and its momentum and all that to the lattice pretty much. And that's why when you actually take the piece of semiconductor and you are in this electric field, you can measure the temperature rises. It's the heat. So in the end, the lattice vibrations, you can measure the temperature. In fact, that is a very big problem today. I mean, so heat is a very big problem in semiconductor devices today. If you have a billion transistors, each of them is carrying current, and you are operating here when the transistor is on, and it's dissipating a huge amount of heat. A lot of h bar omegas are coming out. And typically what happens is the optical phonon will start out, it doesn't have much group velocity, but it will immediately decay into acoustic, and the heat flows as acoustic phonon or a sound wave, it just flows across. So extraction of heat is almost as important today for electronics as making a good transistor, because there are good transistors. Some of the limit is now heat related, and there's so much heat dissipated that it's hard to extract it, and therefore there's a lot of effort now in controlling the heat dissipation by designing transistors in different ways, by tunneling, by all kinds of low power switches and things like that, or metal insulator transitions, or negative capacitance. All these things are meant to reduce the energy dissipation in electronics today. So yeah.
Are the scattering events before saturation, are they also caused by interaction with optical phonons?
Good point. So you mean here?
Yeah.
Yeah. So let me sketch something quick so that it gives a little better picture. And this is something I'm hoping, within first few weeks we will have an assignment with. So what we will do very soon in the class is here. So again, this is effectively a graduate course, so we are going to be very clear on sometimes it's electric field, sometimes it's energy, sometimes it will be something else, but here it is energy, okay? Energy, let's say EV, right? And here's scattering rate, okay, as a function of energy. Right? So what we'll see is there'll be all kinds of scattering events possible. There could be due to impurities, defects in the crystal, typically, the scattering rate we'll see from the kind of the Fermi's golden rule will be proportional to the density of states of electrons, or if it's electron-phonon interaction, it's a joint density of states and things like that. We'll see that. Okay? But typically, the scattering rates start out from 0 for many scattering events, which could be acoustic phonons, could be defects. They will start out from here. And remember, we said typical time for scattering is about a picosecond. So scattering rates will be plotted in 1 over picosecond. That's the rate, right? 1 over tau, right? So 1 over picoseconds. And if it is, so for most defect or acoustic phonon scattering events, it will kind of start out like that, right? Optical phonons will have a threshold, as I was discussing. So it will be, h bar omega, let's say, of optical phonons.
Is that for an acoustic?
Sorry? Yeah.
The first curve, that's for an acoustic.
Oh yeah, so I'm going to kind of club all those things together. You can call, so it would be acoustic or, say ionized donors or defects, kind of all combined together. So, and they might have slightly different dependencies, but, that's kind of a club together at this point. I'm not trying to distinguish different things at this point. And it also depends on things like dimensionality. If you are going in 3 dimensions instead of if you're going 2-dimensional electron gas, it will have a slightly different shape. If you're going in 1D, it will have a different shape and so on. So dimensionality also plays a role. But the main point was that the optical phonon, once you reach the threshold, it really starts out very high, and the magnitude kind of swamps the others. That's really what I'm saying. So essentially, because you can imagine the electron is, the reason for that is all these other scattering mechanisms are ineffective they are very effective in randomizing the momentum of the particle. It can, scatter this way, but it cannot take out the energy. Optical phonons have the capacity to, essentially suck the energy out of the electron system, and that's why. Anyway, so that's one of the reasons. Where optical phonon, an acoustic phonon has, as you know, again a sketch at this point. The phonon spectrum of a crystal will be, acoustic modes and then in an optical mode. So optical mode is what we're talking about. This is our h bar omega optical, about 50 MeV, or order of magnitude like that. Acoustic starts from 0 energy, so from all the Goldstone boson sort of ideas. This starts from, it has no threshold. You can start emitting it, but at the same time, it's also losing very little energy, because the h bar omega is small. Yeah, Jake, you had a question.
Thank you. So is it possible to operate your transistor in the regime before you touch the optical phonon spike?
Oh, definitely. So you will have to address a very strange dilemma at that point. You can always operate a transistor at a very small, but you can see right away that the velocity would be low, right? And that means, in the end, if you look at everything else, the speed, all these things would be low, right? So you are not driving the device to its full capacity, right? On the other hand, if you are way out here, that's also not very good. You're losing a lot. So there's always a balancing act when you are going to make a device, because many of electronic devices, not necessarily just transistors, even lasers, LEDs, they can operate with very high efficiencies when they're almost off, But then that's not extremely useful, So maybe it's useful for some things, but if you want to do the high number crunching and all that, then you need that performance. So it's a balancing act. If on the other hand you want your electronics to be sitting around waiting for something to happen, for 20 years, then you want to operate it here because it's just, low power, and then suddenly there's a threshold and it goes into full computation. So that's a different problem, but you can. It's just there's a reason why we push it to its limit, and that, yeah. Okay, so again, so we will calculate these things, scattering rates, acoustics, phonons, defects, optical phonons, and other things like that. And there's also very clever ways in which you can completely remove some of these scattering events by making heterostructures, quantum wells, and putting dopants somewhere far away and the electrons here. You spatially separate them. We'll look into those things. Okay, so let me also, because we are looking at this figure, just try to complete one aspect of the classical picture of electron devices here. So if I take velocity and I multiply it with the electron density, we get current density, right? Current density, and electric field times the length is the voltage. So current versus voltage of any semiconductor will also look pretty much like that. Right? So you can take, so there will be a linear regime, a resistor regime, and then there will be saturation regime. Again, there are some semiconductors where you can actually get something like that. For example, it will actually increase the field, the velocity will go down. And this is called negative differential resistance. So for them, if I do di by dV, it's actually negative. So that's very interesting. We will discuss some aspects of it. You can make oscillators. It's an unstable situation, So and you can make oscillators and other things. We'll talk about that. I don't want to, spend time at this point on that problem. But the moment I go from here to there, I have n, which is also there are two parameters controlling this. As you can see, one of them is electron density, the other is velocity. The two independent parameters. Just to be clear, they are independent in the way I have set up the theory. The electrons are doing their thing, right? So, but they're independent the way I'm picturing this problem, right? And indeed, the idea of a transistor itself is completely based on this, dichotomy, or the way you can split the two. This is your transport problem, and this is the control of the population of electrons. That is by the gate. This is electrostatics. So you control electrons by the density of electrons by electrostatics, and this is your transport problem, right? So really, I'm also, these are the words. So in reality, the whole thing is obviously a transport problem, the current, right? But I'm trying to say that all the scattering and the details of phonon scattering, etc., are determined by are clubbed into the velocity term, whereas the electron density is you just have how many electrons do you have, right, to do all that transport. Now in a transistor, for example, the one that we were looking here, so the electron, the velocity is typically, as you can see, driven by the voltage that you're applying across the source to drain. So this is a 3-terminal device. The way we make the transistor is I will have a very heavily doped sea of electrons here, a lot of electrons, maybe 10 to the power 20, as you saw it here, maybe 10 to the power 20 here. And then I will have an insulator, and then I have a gate metal. Right. So here's a semiconductor. Now, and I'm flowing in current here, and I'm pulling out current here. So there is a 3-terminal device. I can ground this, and I can apply a voltage across here, and we call it a drain to source voltage, VDS, drain to source voltage. And that, if we forget about all this stuff on top, is what is going to flow the current here. That's what is going to do that, right? I is V. So when I write it here, I should write it V drain to source in a 3-terminal device. So drain to source. And that's going to do that. Now, the gate is a 3rd terminal. So let's say I have electrons that come around here. The gate is controlling how many electrons there are at this interface now, right? So in physically, I have drawn it as a planar transistor. This is how transistors were till the 2010 or something, and then it basically got folded over, right? So now instead of a planar geometry like that, you have an oxide, a metal here, and the semiconductor is a fin. That's what it is. We are looking at the cross section of this device now. So the source is here, drain is on that side into the board, and all around it, that's the gate. Here's the insulator. So why are we doing this? Basically, what we have is a metal insulator and then a semiconductor. If I have a lot of electrons, you can think it effectively also as a metal, but it's a capacitor here, right? So with a capacitor, you have this very nice opportunity that if I apply a voltage on this terminal gate metal here, VGS. Now everything is with respect to the grounded terminal, which is the source. If I apply a voltage, let's say I apply a positive voltage on this. What I'm doing then is it's a metal. Effectively, I have positive charges here when I apply positive voltage on any metal. And how did I get positive charge? Because the battery took some electrons from the metal and it put it back here. So that's so everything is charge neutral always, right? So if I apply positive voltage here, I accumulate some extra electrons here, right? If I apply negative voltage here, I remove that, right? So that way I can go and control by electrostatically. When I say electrostatic, it's just a parallel plate capacitor. I can capacitively control how many electrons there are that are going to do the transport. Okay? And that control, so the number of particles we can control and change it by typically 10 to the power 10, a factor of 10 to the power 10. It's 10 billion. We can change the carrier density from highly insulating to a very reasonably conducting material. So, and we'll see, they are moving the Fermi level inside the material by. So this is the key for switching for electronics today. That you can change the number of carriers doing transport for you by 10 billion. With a very small voltage, maybe 0.2 volts, 0.3 volts. That's all you need to change it by 10 to the power 30. So when you do that, you can imagine now, let's say the velocity also gets affected, but maybe not much. Let's assume the velocity field curve stays the same. But you can see your current versus voltage is changing by 10 to the power 10. So it will go like that, it will go like that, and finally it will be nothing, right? So as you turn, the carrier density is up and down with the gate voltage. So this is basically you're switching it from on to off of the device. And you're doing that by changing the carrier density. It's a very important point. It's not really the velocity of electrons as much as how many particles there are. Right? So that's what is changing this device on and off. And so this is a typical transistor characteristic. When you look at, instead of I, you can call it J, you can call it I. It's current versus voltage. You can pick up any paper or book and see, transistor characteristics, drain current that flows into the drain, or actually the current will flow in this way, but the electrons are going that way. Yeah. And so this is the on-off switching of a transistor in this picture. If you plot it versus the gate voltage, on the other hand, you have to plot it in a linear scale. If you plot it, it will have a certain threshold and it will go up like that. But in a log scale, let's say I get it log scale, it will really switch by 10 to the power 10. That's what I mean. And we'll look into that later. But this is kind of the picture of electron devices and how the transport phenomena will play out in it. Right? Just kind of a more qualitative but overarching picture of where things will go. Okay? Any questions at this point? And maybe there are some. Yeah.
So for this transistor, well, most transistors in practice only permit you to flow current one way from the drain to the source. In this one, there's nothing unique about the drain or the source based on just how we've drawn it, right? So technically, if you hooked up VDS to the other side and grounded the source, if you put voltage on the source side and put a ground on the drain side, you'd still expect current.
Yeah, that's a good question. So the way it's drawn here, it's completely symmetric. It's up to you what you want to call the source and which one you want to call the drain. Yeah. Now for and today's silicon CMOS FinFETs are indeed symmetric. They're all symmetric, and which one you call source and drain depends on things like layout, and you have an N-channel transistor, you have a P-channel transistor next to it, holes and electrons. You want to make a circuit, so that will say, oh, this source should be close to that drain. So that's what determines how you lay it out. But the way it's designed, it's independent. Right? But we'll see that many times we would, for some applications, we would like to break the symmetry sometime. If you want to make a very high voltage device. So we'll see the most high voltage drops on this side, not on that side, because I have two terminals on which I'm applying voltages, so there's a voltage difference, whereas this is not changing much, this is grounded. So I'll do something different on this side. I'll probably pull this out a little bit further to make it a high breakdown. So there are these little tweaks, but for digital electronics, the devices that I use are symmetric. Also from the point of view of, if you want to write, 10 nanometer devices and a billion of them, it'll be difficult to have all of them, precisely aligned and, all that. So they keep it symmetric and they build the circuitry around it. That takes it. Any other questions? Yeah. All right. So if not, all right. So what I wanted to do then is that's my summary. I know that I was planning to do a little bit of more on quantum, but we'll get going on that. We did EMAG. I'll post some of the slides over. So I want to start by just motivating or rather seeing what changes, right? What are the changes we need to do to go from classical physics like this, which already is to kind of qualitatively able to explain many things, but some things, for example, classical physics would have a hard time explaining why we are getting 10 to the power 10 change in the conductivity of a material. It's not trivial because this comes about because electrons are fermions and they follow Fermi-Dirac distribution. Now, Fermi-Dirac distribution is a completely quantum mechanical concept. There is no classical analog to it at all. It arises because of the exclusion principle and things like that. So, and also some phenomena like why does the resistance kind of saturate as you go to very small lengths. This is also not possible really to explain from classical physics. In fact, we'll see that the value of this is of the order of Planck's constant over electron charge squared, h over q squared. It's a quantum of conductance, or so, that's what it's called. Quantum of resistance, or it's called a quantum. Q squared by h is the quantum of conductance, but we'll see this is the order of magnitude, h over q squared. So there's Planck's constant entering here, and that's a completely, very much a quantum phenomena, and it has to do with, electrons instead of really being point charges, as we have talked about in classical physics, really have with them associated wavelength, and they have wave nature. There's wave particle duality to it, and therefore now as it goes through a crystal, there'll be interference, diffraction, all these other things now. So, right? So, all right. So let's see. Actually, let's kind of look at where we will end up after a little review of the quantum. And though I would have loved to do it today, but I think we don't have that much time today. So let me just say that the major problem we'll run into is the moment we go from a particle to a wave. So I'll just so in classical physics, I can write down my total energy of an electron as the kinetic energy plus the potential energy. Right? And I have a ball rolling down a hill, or an electron, moving in a electric field potential created by electric field. The idea is the moment I know my total energy of any particle, be it charged or uncharged, I can essentially find the force acting on it, and I can locate it in the phase space. I can find my x, and I can find the particle at any point in space, and I can find its velocity at that point and momentum along x. And then based on these forces that are acting on it, which you just find from here, gradient of that will give you its equation of motion, and you track it and you find out where it is later, right? So this is x comma p now, and that's x comma p later, right? And that's classical physics. Now the quantum aspect, the biggest problem you run into right away in quantum is the fact that it's a wave means that you cannot have these two determined at the same time. You're not allowed to do that because it's a wave. It's not like the wave is located here. The wave is a propagating thing. It has a spread in space, right? It is. There is no point to which a wave is really associated. The best you can do is like a wave packet. You can kind of confine it a little bit, but the more you confine it, the more uncertain the momentum becomes, right? So that's the uncertainty principle in quantum mechanics. Or really, it is true for any wave. If you try to confine it, its momentum spreads out, and if you try to have a precise momentum, its real space spreads out. Right? The most precise momentum particle is a plane wave photon, which is spread out in all space. Right? It has, but its momentum is completely precise. Whereas, right. So this becomes a problem. And therefore, the law of motion that we started out with, which is force is mass times acceleration, you can see that you run into a problem right away because this assumes that you know your potential, which means you know your r or x, and you know your kinetic energy, which means you know your p. And quantum mechanics says you can't know both of them at the same time, right? And as a result, I can't write my energy like that anymore, right? So I need to rethink how to do that. So what we will kind of get to is that prescription is really the heart of quantum mechanics in many forms. The Schrodinger form is the equation that tells you that the particle, instead of defining the state of the particle by a space, where it is and its momentum, you must have something that combines both because the two are tied. The momentum and x are tied because x times p, minus p times x. These are operators now. Is not zero. They are actually, they become operators, right? And so x and p get tied together in a certain way, and therefore you can't treat them as separate quantities to define the state of a particle anymore, right? So you must have another bigger thing that has both of them inside it, a bigger state function which has both of them inside it, right? Which takes into account both of them, and such that mathematically at least you always satisfy the uncertainty principle, because it always satisfies the wave and particle duality of it, right? And that is the wave function of the electron. And the wave function of a plane wave is a good point to kind of end the class today. Wave function of a plane wave, which is only one electron in the whole universe, there's nothing else, right? Just one electron. But quantum mechanically, the most accurate wave function of an electron borrows heavily from electromagnetic theory. And the wave function looks just like the electromagnetic plane wave. It looks just like that, right? So the wave function of an electron with the psi that you solve for Schrodinger equation will look like a constant times e to the power I. In one dimension, it will be e to the power I kx, and there will be a omega t. And if you have looked at any wave in EMAG, it's the same thing, really. There's no difference. But now you have these two things, tied together in an interesting way, right? So this becomes the state of the electron, and this is the simplest one. And of course, there are many variants of it which we will go through. You put it in a box. The particle in a box will have no net, velocity because it's bouncing back and forth between the walls. So, it will take a sine function or a cosine function. If you put a harmonic, in a parabolic potential, it looks something different. But that's the basic idea here. And from here, you can see that if you plot this sort of a wave function, it's inherently complex, and it must be complex. For a free particle, we're going to get into that at this point, but you're forced to have a complex number here. By inception, it has to be a complex number. A real number cannot do justice to the uncertainty principle here. So, what Schrodinger's prescription is: look, I see a problem in classical mechanics because of Heisenberg's uncertainty principle. So instead of finding energy that way, you solve my equation. Okay, and here's the wave function of the particle, which respects the uncertainty principle. And if you solve this equation, then you will recover the new energies now. Instead, right? So that's Schrodinger's prescription. There is a slightly different prescription due to Dirac, and there's yet another. Well, there are a few others. I mean, Heisenberg and Dirac had the different notation, and then Feynman gave another notation. All of them effectively are describing the same thing. And later on, when we talk about some aspects of topological physics and all, we will look at the Dirac interpretation, because that's a good way to enter that subject. And things like Aharonov-Bohm experiment and interference, the Feynman approach is very good for that, weak localization. So we'll look at all these three aspects of it. But we'll start with the Schrodinger version of it. So we'll start with Schrodinger version. And we'll start with this, and then we will basically find from the wave function what is the momentum, what is the velocity. We'll try to recover this from this picture now, from the quantum mechanics picture. So we are out of time today. A few announcements. So I think a few announcements for the class. All right. So I told you that there will be some travel coming up for me, and turns out I'm away for the entire next week. So that means I'll miss 2 classes next week. And I hope that by the end of this week you reach clarity on which courses you are taking, and I find the time. We'll make up. I mean, we have about 27 classes, or 27 lectures. We'll have 27 lectures. But I want to make up, and I'll try to find times with you. So, well, next week you don't have